Everybody, Dr. White here. Going to talk with you about conditional distributions associated with a bivariate distribution. So let's let x, y be some bivariate distribution. And let's just ask ourselves, what's the chance that x is equal to some specific little x, given that you know that y is equal to some specific little y? Definition of conditional probability brings us right to this. Probability x is x and y is y over probability that y is y. And so the numerator is just the PMF, f of x, y, and the denominator is the marginal of the random variable capital Y at little y. So perfectly sensible concept. So let's go ahead and define conditional probability mass functions. The probability mass function for capital X, given that capital Y is Y, can be written G of little x slash little y. That's how the book writes it. And it's just defined as we did. Of course, that definition only works if the denominator is not zero. We know that probability mass functions are at least zero, so we're just requiring that that be bigger than zero. Similarly, you can define the conditional probability mass function for y given that x is x. The book calls it little h of y given x and defines it in the way that you would expect: chance of y is y and x is x divided by the chance that x is x. And of course, the denominator needs to be non-zero. So you got these conditional probability mass functions. And so you get these conditional probability distributions that they are the PMFs for. And so like, how will you see this written? The conditional distribution of x given that y is y might be written that way or this way for short. Keep in mind, it's not really the, because there's one of these for each value of little y that's possible in this random experiment. Well, each one where there's a chance bigger than zero of that happening. And similarly, the conditional of y given x, that random variable, or that family of random variables, one for each x, is written like this or like this for short. And again, the f's of x does have to be bigger than zero for that to happen. So let's play with an example. How about the same example that we have looked at before with the bivariate bizarre sorcerer? So you'll remember the sample space was x could be 1, 2, or 3, y could be 1, 2, or 3. It was 9 points in the xy plane. And I've got those possible x and y values circled in this little picture, like this one. And I've got the joint PMF values written over where the points are. And I've gone ahead and added up, all possible f's for all the possible y's where x is a particular value, and thus get the marginal for x. So it looks like there's a 1/3 chance for each of the possible values. I've also done the sum of f of x, y over all x's for each y, and I get the same thing. The marginal for y is also 1/3 each time. Okay, so why don't I just compute a few conditional PMF values for you. So here we've got the chance that y is 1 given that x is known to be 3. So we look for the chance that x is 3 and y is 1. So x is 3, y is 1 takes us to here, 1/36. And we got to divide by the chance that x is 3, and that's the 12/36 down here. the 36s cancel, which is kind of like you're just zooming in on this particular set of possibilities. And anyway, you get 1 over 12. Now, compare that to just the chance that y is 1, knowing nothing about x. That was this 1236, which is a third. So you'll notice they're not the same. That goes along with our knowledge we already have about this situation, that the marginals are dependent. Knowing something about x changes your estimate of the chances for y. If you know that x was big, then your chance for y to be 1 has dropped down a good bit from what it was before. How about h of 2 given 3? Similar computations, I get a third. What about h of 3 given 3? Also a third, so that's kind of interesting. I'm sorry, whoa. 1/12, 4/12, and 7/12. And so we're getting not the sames. If we got the not the same just once, that would already be a sign the two random variables are not independent. And here we find that there was always a difference. So it's just illustrating that the lack of independence here is totally illustrated. Before you knew anything about x, there was a 1 in 3 chance for each of the possible values for y. But once you know that x is 3, then you're thinking, well, y is most likely to be 3, and there's only a little bit of chance for it to be 1. And so what we've done here is we've computed the conditional distribution of y given that x is 3. There's also a conditional of y given that x is 2, and there's a conditional of y given that x is 1. 2 more random variables lurking around there whose distributions we could have computed in the same way. Now, if x and y were independent random variables, then these conditionals would not differ in the ways that we've seen. So like the PMF for the conditional of y given x, by definition is this, but because of independence, you could factor out f of xy as f sub x of x times f sub y as y. And then there would be some cancellation, and you're only left with f sub y of y. So that would mean the conditional of y given that x was little x is distributed just like the marginal y is, no matter the x. And similarly, you could demonstrate that the conditional of x given that capital Y is a particular value little y would be distributed like capital X no matter what the little y is. So that's what you would get with independence. You can do conditional means if you like, and so those would be means of the conditional random variables. So like the mean of the conditional random variable y given that capital X is little x, I guess you could also see it written as the expected value of capital Y given little x. So you just sum over all the possible little y's, the value of little y times that conditional PMF if you ever need to do it. And the same if you need a conditional mean for an x given little y. Very same idea. So for example, how about the conditional mean for the conditional variable y given that x is 1? So possible values for y, 1, 2, and 3. We just have to multiply by the conditional probabilities. So we like look back up in, I don't think we've done that. Yeah, we haven't done that. So we'll have to like, I'll find these ones one at a time, or maybe just like, I'll do like one of them as an example. So how do I know the conditional chance for y to be 1, given that x is 1, is 7/12? Well, that would be the chance that x and y are both 1 which is 736, divided by the chance that x is 1, which is 12 over 36. Divide, and you'll get 7 over 12. And so in a very, very similar way, you could get the chance for y to be 2, given that x is 1, is 4/12, and the chance for y to be 3, given that x is 1, is 1/12. And then you could just sum that up, and you're following out this definition here for conditional mean. And it turns out to be 1.5. On the other hand, if x is known to be 2, you can find that the expected value for y is 2. And if x is known to be 3, then the expected value for y would be 2.5. And this kind of follows out the intuition that we've had before, that we've been developing as we've been working with this random variable, that the bigger the x is known to be, the bigger the y is likely to be. You know, that came ultimately out of the fact that there was like a concentration of small x, small y probability here, big X, big Y probability here, whereas it's relatively unlikely to have small x, big Y, or big X, small y. There's also conditional variance. So the variance of one of these conditional random variables could also be written like this. Just by definition, it's going to be the expected value of this conditional random variable. It's a function of capital Y. It's capital Y minus the conditional expected value for y given x squared, given that capital X is little x. And so the way you'd work it out is you'd sum over all the y's, y minus that conditional squared times the little conditional PMF. And similarly, if you had to do a conditional, a variance of a conditional random variable. So let's go back to our example. And you may remember from previous sections that the expected value of the marginal y was just 2. I just want you to note that for a moment. Another thing that would be kind of fun to do is let's just compute this sum. So we're going to sum over all x's. X is 1, 2, or 3. The conditional mean for y given x times the chance for x to be 1, 2, or 3. Let's just do this sum and just see what it turns out to be. So that, by definition, would be this sum here. And we figured these things out. This mean was 1.5. This mean here was 2. And this mean here was 2.5. And the marginal on x was 1/3 each time. And so you're doing 1/3 of 1.5 plus 2 plus 2.5. That's actually 1/3 of 6, which is 2. And so that's kind of interesting. This little weighted average of the conditional means for y, where the weight is the marginal probabilities for x, worked out to be just the mean for y. And this always happens. In fact, it's proven in the book that it always happens. You can take a look at it. It's called the law of total probability. And a nice way of writing it is like this. Because what this is right here, if you just think about it, is here you have possible value for the expected value of y given x times chance of getting that value. So you have the expected value of the expected value of y given x. And that's always working out to just the expected value of y. And so the applications for this are really quite various, and it's quite useful thing. Sometimes when it's tough to find the expected value for a random variable, if you can set up another random variable, and then between the two of them have a bivariate distribution, then you can condition your mystery random variable on the other random variable, find the expected values for each of those conditionals for all the different values of capital X, and then take the expected value over the capital X variable. And that'll give you the expected value for your Y. So we'll do some applications soon. But I want to clear up something that is like not totally as clear in the book as I'd like it to be. The expected value of Y, given that capital X is little x, that's the expected value of an actual probability distribution. Well, conditional distribution, but it's totally a probability distribution. It's just a different one for each value of x. But it is totally a probability distribution. And so its expected value is going to be a number. It might be a different number for each of the different little x's, but it's a number each time. On the other hand, this is a random variable. This little thing that you see here that shows up in the notation here for that theorem, that's a random variable because the capital X is a random variable. Its possible values are these different numbers. And the chance of it having each of these possible values are given by the chances for X, capital X, to be the different little x's. So I just wanted to clear that up because you're going to see this notation here in the book a lot. So a kind of like a pedantic way of writing it out would be this. The chance that the expected value of cap y given cap x is equal to the conditional mean of y given that capital X is little x is the chance for capital X to be little x. Or even more pedantic way of writing it out would be like, hey, let's take a look at the probability mass function for this bizarre random variable. So its possible values, are these, and what's the chance to get each of these values? It's these. So little formula for the probability mass function of this kind of expected value random variable. Another law that's proved in the book is called the law of total probability for variances. The variance of a capital Y can always be found if you pair it with some other variable, random variable capital X, and make a bivariate distribution out of the two of them. And then just work with this, the expected value of the variance of Y given X, plus the variance of the expected value of Y given X. So we'll do some examples with that too. Now, I tend to call this the conditioning technique, and because it very much resembles the conditioning technique for finding probabilities that we looked at way back. If you remember the problem of the roommate and the jeans and khakis, the probability that you're wearing jeans was this weighted sum that looked very similar. And you were conditioning, to get that, you were conditioning on which closet you walked into. Same kind of thing happening here. And so you might also call this law here, sometimes it's called the Conditional Variance Formula. So let's do some examples. First of all, let's say the number n of hurricanes that hit a certain coastal city in the course of a year, let's say that's a random variable. And let's say it has the Poisson distribution with rate lambda equal to 5. And if you remember, the mean of Poissons is the lambda rate. So what you're saying is you're expecting 5 hurricanes per year, give or take some, for a chance variation. And let's say that the damage caused by any hurricane is exponentially distributed with a mean of $10 million. So, working with a kind of two random variables here, one of which is a discrete type and the other one's continuous type. And like we haven't really formally addressed that before. Like we've studied bivariate distributions, which are discrete, and both the marginals turn out to be discrete. And it looks like I'm gunning here for a bivariate situation where one of them's discrete and one of them's continuous. But just go ahead and follow along with me because I'm impatient and I love this example and I want to show it to you. So let's let capital T be the total damage from hurricanes. Okay, so you have your hurricanes, however many, each one of them does their damage, you add it up. You add up the damages. And that's capital T. Could we find its expected value? Well, you can use this conditional expectation, this law of total probability for expectations, even when one of the random variables is continuous. In fact, we'll find in section 4.4, you get the same law even when both of them are continuous. So it's the same idea and the same basic looking proof. So let's go ahead and use it. Let's find expected value of T is the expected value of of T given capital N, the number of hurricanes. So when I look for this expected value here, I'm summing over all the possible values of capital N. Now capital N's Poisson, its possible values are 0, 1, 2, 3, and so on. So I got to sum, little n goes from 0 to infinity. And I've got to have a probability that capital N is little n out here. And inside, by definition of expected value, inside I've got to have the different possible expected values. So expected value of T given that capital N is little n. That's what I stick in there. Okay, I know the PMF for Poisson. So I got a rate lambda of 5, so I say 5 to the n, e to the minus 5 over n factorial. And I got to think about expected value of E of T, total damage, given that you got little n hurricanes. So there's a couple of ways to think about this. One way is certainly to think of it as, well, the total damage is the sum of the damages of each hurricane. So D1 plus D2 all the way up to plus DN, where DI is the damage from Hurricane I. And then you could say, you know what? I think the expected value of a sum is sum of expected values. Now, actually, that's not something we have formally proven for just any bunch of random variables at all. We've formally shown that, like, the expected value of, a linear function of one random variable is constant plus constant times expected value of random variable. We haven't really shown this for just like any random variables at all, but we will in chapter 5. And it seems intuitively just obvious. So we could sort of try to go with that for now. And if we did go with that, then we would say, well, you know what? Each of these is exponential with a mean of 10, right? And so let's see, the mean of a random variable is its theta parameter, so it's really saying theta is 10. And there's n of them, so we should get n times the mean of an exponential with a theta equal to 10, but that's just a 10. So we're going to get a 10n here. Another way of thinking about like what this ought to come to is to say, you know what? Okay, if the D1 plus the Dn is the sum of n independent exponential thetas, wait a minute, we already know that that would have to be a gamma in theta, because you can think of each of these exponentials as the time to wait for the next event in a Poisson process, whose rate is lambda equals 1 over theta. And so this sum here would be the time to wait for n events, and we know that has to be gamma in theta. And then we know the formula for expected value of a gamma is the alpha parameter times the theta parameter in theta. So that way you could get your 10 times n without having to like rely on the fact that the expected value of any sum of random variables is the sum of their expected values if you didn't want to. So one way or another you get down to here. And I guess the 10 can factor out. And then I like look at that and I realize, whoa, this stuff right here is exactly the definition of the expected value of capital N. And the expected value of a Poisson is its rate. So $50 million is how much damage from hurricanes this little coastal town can expect each year. Okay, let's try one from the book. It's exercise number 11. And to keep things officially like correct here, they're dealing with a situation where both your random variables really are discrete. So what you got here is they're pretty abstract. They don't have a specific real life situation. They just say, hey, imagine a geometric random variable with parameter p. So it's like you're tossing a coin looking for your first head, and the chance of heads is p each time. And the conditional distribution of some random variable y given capital X is Poisson, where the rate is that capital X. So it's like this. It's like you've got all these like Poisson random variables, and you want to try one of them, but which one you try is a matter of chance. And here's how you figure out which one to try. You flip a coin until it comes up heads, and you count how many times it took. And then you go to the Poisson whose rate is how many flips you needed. And you try that one. That's what this y given x is like. So what's the expected value for y? So using the conditional expectation formula, well, I look in here, and what's the expected value of y given x? Well, it's the expected value of a Poisson where the lambda is x. But the expected value of a Poisson is the lambda. So really, that just comes down to the expected value of x. Well, x is geometric, and here's the formula for expected value of geometric. Okay. Hey, let's use that conditional variance formula and get the variance of y as well. So that's the expected value of the variance of y given x plus the variance of the expected value of y given x. Okay, let's think about this one. What is the variance of a Poisson? Well, the variance of Poisson is also its lambda rate. And so the variance is x. So we're looking at the expected value of just x. All right, now let's look for the variance of the expected value of this thing. Let's see, well, what is the expected value of a Poisson? Oh, it's the lambda again. So we're looking for the variance of x. So we're adding together the expected value and the variance for a geometric. All right, one more example. Let's say that hobbits are like this. So this is like the Lord of the Rings, and there's hobbits and there's all the other creatures, in the Lord of the Rings. And hobbits are short. And let's just say that the population of hobbits have heights that's bell-shaped, normally distributed, where the mean is 40 and the standard deviation is a 5. Now, usually we use mu and sigma squared. I'm just putting here that's the standard deviation. So the sigma squared is actually 25. And there's also Ents in the Lord of the Rings, and they're tall, tall tree creatures, you know. Let's say that their heights are bell-shaped distributed with an average of 200 inches, give or take 20 or so in either direction, standard deviation of 20. And let's say it's the Shire. And in the Shire, 95% of the inhabitants are hobbits. And the other 5% are Ents who have immigrated to the Shire because they like the nice foresty gardeny quality of the Shire. 5% of them are Ents. Okay? And let's let capital X be the height of a randomly selected Shire person. In some textbooks, they'll call a random variable like capital X a mixed random variable because it's the mix of two other random variables where there's some fixed proportions for how you do the mixture. Anyway, can we find the expected value and the variance of capital X? So what's the expected value for the height of a random person in the Shire? What I'm going to do is find another random variable to condition on and use the conditional expectation formula. And I'm already leaning over and getting a pencil handy because I see like a little typo. The conditional expectation formula would say the conditional expectation of X is the expected value, which I'm missing, of the expected value of X given the thing you're conditioning on. So there should be like an E right here and then parentheses around that. Okay. Now that random variable type that we're conditioning on is two possible things. It could be a Hobbit, it could be an Ent. Okay. And the chance of a Hobbit is 0.95 and the chance of an Ent is 0.05. So that expected value of the expected value of X given type would be this sum here. Expected value of a normal random variable 40, comma, standard deviation 5 times the chance of that plus the expected value of a normal 200 standard deviation 20 times the chance of that. Now the expected values are 40 and 200 respectively, so we just need to compute that. It turns out to be 48. Ta-da. So before I forget, I'm going to go ahead and correct that. Okay. Now let's go for the variance of X. So that's the expected value of the variance of X given type plus the variance of the expected value of X given type. So before I can get this kind of quantity, I really have to understand that that is a random variable and what its distribution is. So type, could be two things. Could be Hobbit or it could be Ent, right? Now suppose that you are Hobbit. What's the variance of your height if you're a Hobbit? Well, the standard deviation for your height was 5. So the variance is 25. What's the chance you're a Hobbit? 0.95. Now, the other possibility is you're an Ent. Type could be Ent. In that case, what's the variation of your height given that you're an Ent? Well, standard deviation for height of Ents is 20. Variance would therefore be 20 squared, which is 400. And there's a 5% chance of it being that. So this little table here is a table for the probability mass function for this discrete random variable. And we're going to need to get its expected value. So I'll do that in a minute. Let's head over here for variance of expected value of X given type. Now again, that stuff shaded in is a discrete random variable with two possible values depending on whether type is Ent or type is Hobbit. Suppose type is Hobbit. What's the expected value of your height if you're a Hobbit? It's the 40 inches. 95% chance of that happening. Suppose you're an Ent. What's the expected value of your height if you're an Ent? Well, that would be 200, and there's a 5% chance that your type is going to be an Ent when you're randomly picked for each height. So this is the probability mass function for this discrete random variable. Now, we're going to be asking for the variance of that discrete random variable. And one way to do to get the variance, you need the mean, right? No matter how you do it, whether by the definition or the shortcut formula. So I'm going to very quickly calculate the mean of this random variable. And I'm like, oh, wait a minute. Already did that right up here. Same computations, already done it. It's 48. Now, let's head for that variance of x. So what we got to do is we got to get the expected value of this guy right here. And so we just apply expected value definition. Value times chance of value. Sum it up. Ta-da. Now over here, I got to get a variance. So I'm going to kill my face. Or can I move my face? Yeah. Now over here, we got to get a variance. And I'll use the definition. So we'll just use straight definition of variance, which is expected value of x minus its mean squared. So I do value minus the mean squared times chance of the value minus the mean squared times the chance of the value. And so I got to add up all that stuff. And so I did it with a calculator, and I got 1259.75. 1259.75. Which is not a terribly interesting number. Its square root would be, I don't know, more than 30, less than 40, let's say about 35. And so like the typical height, this is like saying that the typical height of a Shire person is like 48 inches, give or take 35 inches or so, which sounds kind of ridiculous. And it is, because this distribution this mixed distribution is not bell-shaped. You got a 90% chance for a 40-inch roughly person, and a 5% chance for a 200-inch person. It's not like there's really like a much typicality to what a height would be. But we'll investigate that further with some R work. How about we finish up? I think I'm done with the written part of the notes. So we'll do some R work in another screencast around conditional random variables. So see you later.